We start with vocabulary which we are going to need for the subsequent discussion. This word impedance, the difficulty a wave has in moving through a medium, and here is the definition of impedance, that the medium has a displacing force causing the displacement, and if as a result of that force you get a very small velocity with which this is picking up, then it's hard for the wave to go through that medium. You would put a small number here in the denominator that makes the impedance big. And contrary, if for that same force, if you got a large displacement velocity, what would that mean for the impedance? Please fill in the worksheet. Next, I want to look at reflections, and I have a wave moving through this medium. That what it is the displacing energies are moving through the medium, but when that wave gets to a fixed end, it tries to displace the end. But this is a fixed end. It cannot be moved, and so the displacement velocity is going to be zero. In fact, the impedance of a fixed end is infinite. But what happens is the wave with its displacings tries to push the medium up, and there is a reaction force from the fixed end, and it is as if that reaction force is the source of waves, and the reflection you get is an inverted reflection. You must learn that. I hope this helps it to make sense, but at a fixed end you get an upside down or an inverted reflection, or we say it is a reflection that is half a wavelength out of phase. That is, I sent in a crest. Oh, come on. I sent in a crest, and the reflection is going to be a trough, half a wavelength out of phase. However, if you send an unfixed end up to this end, and what my picture is instead intending to represent is a hoop that's around a greased pole, so when that displacing energy tries to lift the hoop does go up. And in this case, what you're doing is entering a medium which has no resistance. That effectively you get near infinite displacement velocity from that restoring force, that we're entering a medium of no impedance. Here you're entering one of infinite impedance. You enter a medium of no impedance, and this time the reflection would be upright. That it picks it up and it puts it back down, and boom, the reflection is in phase or upright. Okay, now, if what we just established is if you go through a medium and you enter an end where there's nothing there, it has no impedance, then the reflection, well, all the energy will be reflected because there's nothing to put it into, and the reflection will be in phase, and no energy will go on. Similarly, if you come up to a fixed end, then you are entering a new medium of infinite impedance. All the energy will be reflected. It will be reflected inverted, or a half a wavelength out of phase, and none of the energy will be transmitted. Now for these three in here, energy will be transmitted. That what is going to happen is, I would say it's partial. Some of the energy will be reflected and some of the energy will be transmitted. It turns out that the amount of energy that gets reflected increases as the difference between the two mediums gets bigger. At this great extreme, going to nothing or going to infinite, all of the energy gets reflected, and the closer you are to that extreme impedance, the more energy gets reflected, and the less energy gets transmitted. But what I would ask you to put in here would be that here you're entering a medium of less impedance, and I would say that part of it There's a partial reflection, a partial transmission. This governs how much of it gets reflected, and that what, as you come up here, is this going to be more like coming up to an unfixed end or coming up to a fixed end? Do you expect the reflection to be in phase or inverted? And you go ahead and fill in the rest of this table. I hope I don't spoil some, that if this transmitted part is always going to be in phase, it doesn't make sense that you would send a crest up here and what would pass into this medium would be a trough. No, it's going to be a crest. So always the transmitted wave is going to be in phase, and it's inverted if it's entering a medium of greater impedance. Here would be the greatest impedance. If it's entering a medium of lower impedance, then you get an in phase or upright reflection. So you do this problem, you need to know that glass has higher impedance than air does for the passage of light. Perhaps you could have guessed that. Okay, so here are a series of time snaps that there's this wave going up to a fixed end. Here it has reached it. That's a quarter of a wavelength that's moved forwards, and here it would have liked to have gone on into the new medium, but it can't because there's this fixed end. So all of that energy that wanted to go on gets reflected, but because it's a fixed end, it gets reflected inverted. And if you look at this incident energy and this part which has been reflected, you can see that everywhere in that last quarter wavelength, those two are going to superimpose to add to 0. Now in the next slide, the wave would have liked to have gone forward by a half a wavelength, but there's this barrier here, and so it gets reflected. But it is a fixed end, and so the reflection is going to be inverted. Now if you look at the incident in black and the reflected in red, you can see that they add up to a doubling of the displacement all along this region. In the next, the wave would have liked to have gone here, but it can't. It gets reflected. But because it's a fixed end, that reflection gets inverted. And again, if you add the reflected energy to the incident energy, you can see that everywhere it adds up to 0. And then I continue that process for subsequent quarter wavelength advances of the wave. And what we see is that here where it's a fixed end, you have a point in space where there is never any displacement. That makes sense, but that has a name and you know what it is. This is a node. Come back a quarter of a wavelength and we have 0, double up, 0, double down. That's an antinode. Come back another quarter of a wavelength and it's 0, 0, 0, 0, 0. Oh, this is a point where there is never a point in space where there's never any displacement. That's a node. And from this we need to get the fact that the distance between adjacent nodes is a half a wavelength. Specifically, if you give it enough time, this whole string will come out looking like this, with these nodes half a wavelength apart, antinodal regions in between, and you lose. All it seems to be doing is bumping up and down here and standing still there, that you lose the sense of the wave, the incident wave coming in and the reflected wave going back. We call this a standing wave. I'll show them to you in class. You will see very much that they seem to sit still. Okay, so I want to look at the standing waves, the resonance that I would get if I excited, say, a guitar string that was fixed at both ends? Well, if it's fixed at both ends, then those are points in space where there's never any displacement. You're going to have a node there, but between two nodes there has to be at least one antinode. And so at one point in time, the guitar string would look like that, and at subsequent points of time, it would take all these other positions. When you draw this for me, I would like you to draw the boundaries of this envelope, but we get this standing wave. How far apart are these nodes? Indeed, and so the wavelength is going to be twice L, if that is half a wavelength. Then we come to the next, and still fixed at both ends, so it's going to be nodes at both ends, but to get to the next, we add another node in the middle. And I hope that you can draw that. Go ahead and give it a try. Stop the show. You have started the show again, and I hope this is what you drew, or something very similar. And what is the wavelength now? Indeed. And the next picture, a node at both of these fixed ends, but we add one more node in the middle. Stop the show, draw it. This is what you should have gotten. And that I have divided L into 3 equal parts, and it takes 2 of them to make a wavelength. So I hope you can see that this is 2 over 1, 2 over 2, 2 over 3. The next one, yes, it's going to be 2 over 4. But these are called harmonics, these overtone, these subsequent pictures that we get. When the Greeks first studied this, they were interested in harmony. They were interested in why certain tones sound good together. Indeed, these 3 tones, if you played them together, would make a lovely chord. Why, said the Greeks. But of course, if you are they're called harmonics, and if it's sound, then you can also call them overtones. We don't hear wavelengths, so what we're interested in is the frequencies. What is true about the frequencies here? And of course, what we need to do is to bring in the velocity. We're going to use the fact that velocity is equal to frequency times wavelength. Then I did a little division. And so this one, at any rate, if you listen to the frequencies, there would be this lowest frequency, and we call that the fundamental. It corresponds to the longest wavelength. The longest wavelength, that's going to be the lowest frequency. This one, having half the wavelength, is going to have a frequency that is twice, and we call that the second harmonic. This one, having 1/3 the fundamental wavelength, is going to have 3 times the fundamental frequency. It's called the third harmonic. Indeed, the names for the harmonics, the nth harmonic would have a frequency that was n times the fundamental frequency. Okay. Here is another scenario where instead of both fixed, one is fixed and the other is unfixed. So here where it's fixed and it cannot move, it will not move. You're going to have a node there, but here where it's unfixed and it can move, it will move. You're going to have an antinode there. You could see if you could draw that. Stop the show. You started the show again, and this is what you should have drawn on your worksheet. What is the wavelength of this? Well, between adjacent nodes is a half a wavelength, so from a node to an antinode is a quarter. This is going to be 4L. I'll write that. Now, the next picture. Well, just add one more node. Keep a node here at the fixed end, keep an antinode at the unfixed end, add one more node. I see you've done that because you started the show again, and this is what you get. And despite my scribble, that 4 lost itself. So, what have we done? We divided L into 3 equal parts. How many of them does it take to make a wavelength? Each one of them is a quarter of a wavelength. So it takes 4 of those thirds of L. And the next one, add another node. And this, I hope, is the picture that you drew. Not being lazy and letting me draw them. And what is that? We've divided L into 5 equal parts, and it takes 4 of them to make a wavelength, 4/5. Then this, again, being the longest wavelength, would be the lowest frequency. That would be the fundamental for this pipe. But this, having 1/3 the wavelength, would be 3 times the frequency. That's the 3rd harmonic. And this would be the 5th harmonic. Very important. When you're dealing with two ends which are different, you do not get even harmonics. Only odd harmonics. Don't let me trick you on that. Very important thing to remember. If both ends are unfixed, then you're going to have an antinode at both ends. Has to be at least one node in the middle. So this then would be the longest. How far is it from there to there? Indeed, half a wavelength. So this would be 2L. Here would be the next picture that you get. We add one more node. This would be L. Here would be the next picture. Add one more node. That's, we've divided L into 3 parts, and it takes 2 of them. So this is 2/3. It's just like before. This is the fundamental, 2nd harmonic, 3rd harmonic. So if the two ends are the same, you get all of the harmonics. If the two ends are different, you only get the even harmonics. Very important that you appreciate that the wavelengths that fit or resonate are determined by the geometry, how big L is, and the nature of the ends. Now, if you want to get into frequency, we have to bring in the velocity with which the waves propagate. So that would be a 3rd quality that determines the frequencies, but only these two to determine the wavelengths. Okay, on to sound. A tree falls and nobody's there to hear it. Doesn't make any sound. And this is, of course, a wonderful, fun question to argue about until some spoilsport says, well, what is your definition of sound? These are just silly. We can argue about them if you like. I probably don't have time. So my definition of sound, what is the definition of sound? This is the definition we're going to use in our classroom. Something that I can hear is what I mean by sound. If you blow on a whistle and it doesn't make any sound, then it doesn't make any sound, even if the dogs are going crazy. So what frequencies do excite the human ear? And the classic answer to that question is between 20 and 20,000 hertz. So that will be the range of sound, and below that will be sub-sound, and this will be ultrasound, but it will not be what we will call sound. Consider that if this is the air and you're sending a sound wave through it, if you take a molecule from the gas and displace it transversely to the propagation, there is no restoring force. And so to have elasticity, to send a wave through here, it has to be what we call a pressure wave or a compression wave. That we mash the materials with a slinky. We mash the material together to make a compression, and then the returning to normal pressure causes that's the elastic property. Here you have below normal pressure, call that a rarefaction, and then it returns. And if you put a receiver in the direction that it propagates up to it, then when you get a high pressure, that will push the eardrum in. When you get a low pressure, the pressure inside your head will push the eardrum out, and so your eardrum will vibrate with exactly the same frequency as these high and low pressures. So we recall that the velocity of a sound wave depends upon, and I'm not going to put the answer here. I hope you have been able to put it on your worksheet. And the answer was it depends solely upon the medium for a non-dispersive medium. But it turns out that beyond sending a wave through a sound wave through water or air or steel or whatever, it also makes a difference to what the medium is, what temperature the air is. For every degree you go above zero, the velocity of sound increases by 0.6 of a meter per second. Every degree you go below zero, this becomes smaller by 0.6 of a meter per second. You will not need to memorize that, but you probably will use it so often you will get to know it. So will you please do this problem and recall that with an echo, it both has to get to the iceberg and bounce back in those 4 seconds. Vocabulary. Power. We learned this in the fall. Rate of doing work, or the rate of energy transformation. I would like to speak of it now as how concentrated the energy is in time. For intensity, we mean how concentrated the power is in space. If you take a magnifying glass and you shine light through it and squeeze all that light into a small area, then that's very intense. Loudness is not a measure. It's not a physics quantity. That it's a judgment. When your parents say that your music is too loud, it is too loud. You disagree even with yourself. You get into your car in the morning, and if you left the radio on the night before, it will be much too loud, because you in the morning disagrees with you of the evening on what's the right volume for the sound. But Alexander Graham Bell, trying to make a hearing aid, wanted to know how to, he needed to measure loudness, which was not an objective measure. So he invented this new thing called intensity level, which is supposed to mimic when we perceive it to be twice as loud, the intensity level should be twice. And it turns out that it is a logarithmic, it is an exponential relationship, that if the intensity becomes 10 times this threshold of hearing, if it's 10 times as much, then we say that there is 1 bell of intensity. If it's 100 times, then we say that there are 2 bells. So we take the ratio of this intensity to a threshold of hearing value, take the log of it, base 10, and that's what we mean by the intensity level, and this very closely mimics our perception of loudness. But it turns out that bells are a little bit big. And so we like instead to measure intensity level in tenths of bells, known as decibels. So in fact, a sound whose intensity is 100 times as strong as the threshold of hearing has an intensity level of 20 decibels. And this formula that you have here, we could replace it with this one, which is the one I will put at the top of the page. You do not need to memorize this formula. You do need to be able to work with it, and it's hard to work with. But this 10 is here because we're measuring the intensity level in decibels. You have this on your sheet, on your worksheet, and please, I just said that, but it's there for you to look at, especially as you do this problem. That should be pretty easy. This problem is going to be pretty hard. I believe, I hope I'm right, I'll write it on the worksheet. This threshold of hearing, this I naught, I think is 10 to the minus 12 watts per square meter. So, and that should say per square meter. My bad. That should not be discounted on that account. Okay, we are going to do a lab where we're going to hold a tuning fork up above this tube, and we're going to get resonance. we're going to get an antinode at this open end and a node at the bottom end. And you might think that we would also get this form of resonance and this form of resonance in the tube, but we will not. All of these overtones would occur if you blew across the top of the tube. Then, then you would have the fifth harmonic and the third harmonic and the fundamental. But that's not what's going to happen in the lab. We're going to make a frequency and see if it fits, if its wavelengths fit. Very important detail, however. The reflection here happens because of a change of medium. It happens here because of a change of medium at the surface of the water. And this change of medium is because of a change of impedance. Inside of the tube, there's one impedance for air, and out here, there is a different impedance. And it turns out we have discovered that that change of impedance does not happen at the top of the tube. It happens at a hemisphere at the top of the tube. And what we are going to do is come up with an empirical value that it appears that that reflection happens at 4/10 the diameter of the tube. And so the wavelength here, well, that's just a quarter of a wave that I've drawn, so we're going to multiply that by 4 if we want to get to the wavelength. But the thing we're going to multiply by 4 is L plus this end correction of 4/10 the diameter. If you have a tube that's open at both ends, then the reflections will occur beyond those ends by 4/10 of a diameter. How far is it from here to here? You were right, half a wavelength. So a full wavelength will be twice this distance, which is L, plus 4/10 of diameter at the top and 4/10 of diameter at the bottom. Okay, take those ideas and do this problem. If you pluck a guitar string, it will vibrate at all of its harmonics. But if the whole of the guitar was here, what would that mean as far as how loudly you would hear the third harmonic and how loudly you would hear the second harmonic? And if you put the whole here. So you do that problem. The fact is that when you pluck the guitar string, what we are conscious of hearing is usually the fundamental. But subconsciously, we do hear all of those harmonics. Here is a sort of an illustration of that. Here is the green would be the fundamental, the blue would be the second harmonic. If you add those two, superimpose them, you get this red resultant wave. But notice the distance between those two crests is the same as the distance between these two crests. It's going to be the same frequency that you're hearing, but it won't sound the same as just pure fundamental. It's going to have these interesting little things in it, and that makes for what we call the timbre of the instrument, how those overtones layer on there. That is what I've just been saying. And the result is that because a violin emphasizes the overtones differently than a viola, they have different timbres, that causes a violin and a viola to not sound the same. Here is an example that I just made up these numbers, and then I made a spreadsheet and I put them in, and here would be the fundamental. Here is the second harmonic, 1/5, 20% the amplitude of the fundamental. In green we have the third harmonic, 7% the fundamental. In blue the fourth harmonic, 12%. And then I did these different numbers for the viola. And you can see we get very similar resultant waveforms, but subtly different. And it is those subtle differences that permit you to say, no, I know that's the same note those two instruments are making, but they're not the same instrument. And that one there is a viola. Okay, thank you.